Chemistry in Society, lecture of Chapter 1 from Hill's Chemistry for Changing Times. Speaking, Dr. Tania Cordova Santiago. So, in the first chapter, we're going to be introducing some concepts. Essentially, we're going to be talking about what is science, chemistry as a discipline, technology, what's alchemy, and the difference between these terms, the importance of green chemistry and sustainable chemistry. Again, what's the difference between those terms? Hypothesis, scientific law, scientific theory, scientific models, and explain the relationships, their relationship in science. Other concept that is interesting for us is the risk and benefits, so good and bad things. What is the desirability quotient? Then we're going to be talking about basic and applied research. The difference again between those two terms. Difference also between mass and weight. What each of these terms mean. What is physical and chemical change? What is physical and chemical properties? And we're going to classify the matter according to its state. Is it a pure substance? Is it a mixture? Is it a compound or is it an element? So, moreover, we're going to be talking about measurements. So, when we make observations, we need to do measurements in science. We want things quantitatively. So, what units are appropriate? What are the standards units? How do we do this observation? And how do we convert units? Then examples of that, we're going to be doing the definition of density, calculating density for mass and volume. And also, if you have other two variables, for example, if you have density and mass, how do you get the volume? Then distinguish between heat and temperature. Um, Displaying how the different temperature scale are related. So we have the Fahrenheit scale, which we use and we're more used to. And then we have in more scientific use the Celsius scale that the absolute temperatures are in Kelvin. So we're going to be talking about that and the use of critical thinking to evaluate claims and statements. Finally, in all of the chapters of this book, Hill's book, there are applications of green chemistry because we're interested in how we can help preserve our environment for future generation, which is a goal of sustainable chemistry. Now, science is everywhere, and we have science, and particularly chemistry, in many things, such as, for example, say combustion, when you burn wood to make a fire, when something rusts, so the iron becomes rusty, there's something going on that relates to science. There is a chemical reaction that's happening. When you eat your food in the digestion process, there are chemistry, there are reactions there. The food itself, there's uh, chemical compounds. Photosynthesis, the plants, what compounds are there. The batteries are also electrochemical processes. Fermentation to have your wine or your beer, more chemicals, more chemical reactions. The things that you use to wash your hands, the shampoo, wash your clothes, all of that. And that is everywhere pretty much. Now, but we have science and technology, two things, and we want to understand the differences. Science, we want to understand the principles of things that are going on in nature. Whereas when we have technology, we want to apply something. So technological is more factual, and we have a philosophical aspect. And science brings that when it formulates theories to explain things that is behind. So theories explain why. We're going to be talking more about that. So technology then is when you have a direct application to solve problems. Science will do more speculation, will try to explain things, but through observation, and there is a method to do that. There is something that we call a scientific method. So all of these things are they are related, chemistry is what we have in this class, chemistry in society. Chemistry is a discipline of science. And the essence of chemistry is matter and its changes, how it relates. So the behavior of matter and how it changes. And that's what is chemical reaction. So we have these three things: science, which is more philosophical, explaining why; technology, which is more applied; and society, all of that. We need all that in our society. That's the name of our class. So, and here we have to say views about science. So, the Baconian dream is about Francis Bacon. He is a philosopher that said, ideally, science in general will help to solve every problem in the world. That was his dream, to increase happiness and prosperity. On the other end, we have the Carsonian nightmare, and this is Rachel Carson, biologist, and she published something in Silent Spring in 1962, and because she was very much concerned about the use indiscriminated of pesticides, and that could threaten all life. So we have this to view: the more optimistic, we will solve all the problems, and the bad, that we can have problems destroying everything if we're not careful. And precisely that's the ethics here in science. We love making discovery, explaining things, but we gotta be careful how we use that to the benefit of mankind and so nature. And regarding that, making sure that we have preserved all of our resources for next generation is the goal of sustainable chemistry. In sustainable, and this time I'm talking specifically about chemistry. So we want to, the goal again, preserve all of the resources for future generation. Now, when we talk about green chemistry involves the use of materials, reagents, and things that will not harm the environment or that produce the minimum amount of waste. So, in a sense, working at green chemistry is also sustainable because the least waste that we make, uh, less dangerous things we produce, then we're making it more sustainable because we're helping preserve those resources. But there's some overlap with this concept. So here have in green chemistry we use green solvents, we use things, and also we have technology helping us recycle. So there is green engineering involved in the recycling processes and purification. Now, here we have what is science in general. Every science, chemistry, biology, physics. Science is testable, meaning that we can design experiments and put it to a test. Uh, it is reproducible. When we design an experiment, we want to reproduce the results and draw conclusions from that. Explanatory is that it seeks for explanation and even make predictions. Um, Also tentative, but so there is the cyclic. Here we are making observations, and from that observation we gather a lot of data. We have questions, and with those questions that we want to answer, we formulate a hypothesis, and to test that hypothesis we design experiments. Then the outcome of the experiment is analyzed, and we have conclusions that can then be lead us to formulate a theory. But the collection of data, and then after the analysis, maybe first we get a log, but now we're going to be talking about what is a scientific log and what is theory. But for example, a scientific hypothesis. What is the hypothesis? So it is a testable explanation of the observed data. We have some observations, and we think of an idea that we can test. That's the hypothesis. And so in the scientific method, that will be your first step: observation. We have a question, and here I say, in this particular hypothesis, my question: those water affect plant grow? Is it? So we have that question and that hypothesis that yes, it would, but I need to test that hypothesis. So I do experiments. In that, I gather some data. I study trends, and I get my results, and from that and the analysis, we can draw conclusions and even formulate laws and later on theories that help us explain. But this hypothesis is that testable explanation. Now, when you have a large amount of data and you can summarize it particularly into something in a mathematical form, you have a law. And so you have a large amount of data describing something like the law of gravity, the law of conservation of mass. And here we have an example, is Boyle's law, which we're going to study in the gases chapter. And that says that essentially the product of the pressure and the volume equals a constant. This is something that it has a mathematical form that summarizes a lot of data observation. Now, what is different with the theory is that the theory is a model, is some explanation, is the why. So the scientific law is describing. It may be in a mathematical form, as we have here. The theory tries to explain things, why things are that way. And theories are never absolute. We can find data somehow later that actually is against what is predicted by the theory, and maybe the theory needs to be modified. But that's the idea. So science works in a way that is circular. Now, in science, we use something called scientific models, and these is something that you can see, you can touch, maybe, and that help us represent processes or things that we cannot see. And so, for example, here you have a beaker that is a glass container with water. And here this has more, this has less. But obviously there's some amount of liquid and gas. But the model is this little circles here are models for molecules, representing molecules. That's a scientific model. Right. So here I have other type of models. The model of an atom in the Bohr atom we're going to study later. Molecules we can build molecules with um, models that are stick and ball and some more that is more compact, like a sphere, some like just a draw in 3D, a drawing. Other models representing electron delocalization, a lot of things. Even if you have this in your home or in your school, this map is a model. You don't see the whole Earth, right? But this helps you visualize. That's a model. These models on the right hand side represent the human anatomy. Again, things that you're not seeing directly. But after a lot of research, you can build that model to help us understand how things work. This is like a solar system model. All right. So now we have molecular modeling. So molecules themselves are groups of atoms that are held together by bonds. But we have ways to represent those molecules. And here is where we have, like this, for example, models, 3D models could be ball and stick, or it can be just like fields, um, space filling spheres. This on the right hand side is a DNA molecule, but here actually we don't see the molecules of the atoms. We're representing something else in the structure, the helical 3D structure. So these are molecular modeling. So models explaining molecular structure. Now, science has this limitation. Science needs to be observable, so it's limited to that. So we need to have observations that we can test and variables that we can control. So because to make things reproducible, we need to, for example, when you're running gases experiments, you need to keep things at a constant pressure and need somehow to be able to measure volume and temperature and things like that. So you need to be able to observe or measure indirectly somehow, and you need to control variables. Other things that science doesn't have is like science is not judgmental. Science is not good or bad. It's us who need to value that. We need to evaluate that and how are we going to implement scientific discoveries for the good. So science has facts, but that's your observable, right? And now there are in science. Remember, science is you have you want to know why things happen the way you make your hypothesis, your experiment, and so forth. And technology will apply things to solve specific problems. When we do that, we want to evaluate what is the risk and benefits of everything. And so here we have a quantity that measures that. That is the DQ, uh, and that is dividing benefits over risk. There's some it seems abstract, but we know, for example, here we have things such as evaluation of a number of things in the risk of that happening, so the probability. Well, those are diseases and tragedies, but when we make a discovery, we want to know the impact that that can have, good and bad. Okay, so now chemistry is central to many things. So in this picture, you see well, you can explain why some things are toxic. We can explain how drugs work or understand their structure, neurology, the structure of things, a lot of things. So everything has chemistry because it has molecules. And the basis of understanding that is chemical processes, the changes of matter is what we study in chemistry. So that's why this is relevant for you and that we have this class chemistry in society so that we have like a survey and we understand the scope of chemistry. All right, so we have in science, we have research. There's people dedicated to that. And there is two different type of research. Applied research that seeks to solve specific problems. Um, here we have an example in your book about George Washington Craver's work. He was a scientist that wanted to design a lot of things. He developed a lot of products from peanuts. And that's very specific, but you can also say, let's do a research to improve the gas that I put in my car. So that is less toxic and things like that. All of that is applied, and so it's applied research. There's people dedicated to that. But also, it essential to the advance of society is basic research. And that is science research that is not directly applied, but can help us explain a lot of phenomena that later on can be used to do applied research. So we understand in things the basics, and that basis can help us then do some applied research to solve specific problems. And so here is a picture of Gertrude Ilion that she worked with purines, and that was essentially understanding the cell in this world. And that was basic research. But now there is a lot of applied research in genetics, for example, CRISPR technology. Uh, now, let me go back one slide. I said, well, I don't know that I can. No. So in applied research, for example, you may have seen the movie Oppenheimer. There was a lot of research going on in nuclear decay and radioactivity. We're going to touch bases of that when we study nuclear chemistry. But the fact that that was started as basic chemistry, but then it was applied to something else, like energy, and produce energy from in nuclear plants and bad things such as the atomic bomb. Okay, so central to chemistry is the study of matter and exchanges. So all of that. And chemistry is such a large discipline that we have divided in fields. And here we have organic chemistry, more related to things that contain carbon and hydrogen and other atoms, but a lot of related to more to biochemistry and life. And but we have inorganic, physical, biochemistry. Here you see a lot of branches. But chemistry again studies matter and how it changes in chemical processes. Now,
Matter is anything that has mass and volume. So what's mass now? There is sometimes there's some kind of misunderstanding and people use the terms mass and weight interchangeably. They're not. Mass measures the amount of matter. We can say how much stuff is in it, right? So that amount, the measurement of the amount of matter, that's what mass is. And weight is a measure of the gravitational force on that matter. For example, here I have a picture of an astronaut for your good. But the mass of that, say that it has 50 kilograms. Well, the weight of that you will need to calculate with the effect of gravity, which is in there it's 9.8 meters second square over second square, and you calculate the gravitational force. That's the weight in newtons. So weight is that force, whereas mass is the amount of stuff, say, in kilograms. But since in Mars, for example, the gravity is much lower, as we can see here in this picture, then um, the actual weight will be much less. Okay? And so now we have properties that we can measure in their different type of properties, let's say. And so some properties we call physical, and they have to do so specifically no chemical changes, no not modifying actually the nature of the molecules that are there in its essence, not changing the substance. So we have properties such as the color, the mass, so the amount of substance, and the weight related to gravity, right? So, but we also have other type of properties that we're going to talk later, which is the chemical properties. But other examples of physical properties, we have the temperature. We can measure that if the object is cold or um, um, hot. The mass, again, the amount of substance, matter. The color is also intrinsic, it's physical. And sulfur is yellow, bromine is liquid, is reddish brown. Okay. It tastes to something is sour, like lemon. Bases are bitter. The odor is also a physical characteristic. And here you have hydrogen sulfide, smell like rotten eggs, that's terrible. But some esters such as benzyl acetate smell really nice. This is jasmine, and we have other esters that used in the food industry actually that smell like bananas or pears and things like that. Other properties that are physical are boiling point, melting point, hardness. So something is really hard, like the diamond, or something is soft that can be scratched, such as sodium metal. Density, which is a quantity that we're going to learn about, is also a physical property. Now, chemical properties involve things that are changed. The substance changes into something else, and so forming new substances. So, for example, iron rusts. So, iron reacts with oxygen and forms this rusty cover, so forms iron oxide. Carbon can be burned. You have coal, it can burn, and it combines with oxygen and it can form carbon dioxide. Silver, if you have had anything on silver, silver tarnish, and it tarnishes because it combines with oxygen. And more things like that. So it involves a change of the nature of the substance, changes into something else. Those are chemical properties. So here we have a small summary. Again, physical, you have color, length, we have density, volume, opacity also. Here you have acidity in the chemical properties, acidity, reactivity, flammability, toxicity. All of that is uh, chemical. Now, any examples of physical, uh, so physical properties can change. And what are physical changes? So we have the substance, the identity of the substance is not changed. It's not changed into a different molecule, let's say. The substance is the same, but it may change from liquid to gas, such as, for example, when you're boiling water and it turns to water vapor, and this is evaporation, but it can come back and condense into a liquid. That is a physical change. And here you have an example of melting, freezing. So if here a cube of ice melts, that is melting. But oh, here in the bottom, melting, so liquid, solid to liquid. Or if you put a water in the freezer, then it will turn into a solid. That process is freezing. All of those are physical changes. Here you have another change. Solid to gas directly is called sublimation, and the opposite is deposition. That is, for example, have you had in a or you know anything about dry ice? That's carbon dioxide in the solid form that actually can sublime and is very cold. All right, so and we can classify matter according to its states, as we have seen. So we have what we know that water exists as a fluid, liquid, but also exists as ice when it's very cold and water vapor. So the states of matter, we're talking about solid, and solids has a definite shape and volume. And liquids are more fluid, and those fluids have a definite volume. You can put it, but you need to put it in a container to measure the volume. And depending on the shape of the container, the liquid will have that shape. Uh, and so no definite shape, but a definite volume. And finally, the gas, molecules that are more separated. It doesn't have a definite volume or shape. It can be compressed. And so these are the states. So solid, liquid, gas. And here in this picture, you see in the solid, notice particles very close together, not mobility. So, and here this is in the shape of a cube, so definite volume and shape. Liquid, you can have it into this container, this beaker, or in another flask, and it would turn into the shape of that flask. But same volume. The gas can be in this container under pressure, or you can release it into a much larger container. So no definite volume or mass. Now these are examples of more things about matter. Because matter here, all matter, you can have substances that are pure, say, or mixing things, so mixtures. Substances can be elements, so one single thing. For example, here you have gold, a gold coin, right? Only gold. That's an element. But you can have also compounds, and compounds are made of more than one element. And here, the water is a compound. It's made of two different types of atoms, hydrogen and oxygen. So again, pure substances could be elements or compounds. In our mixtures, depending on how we see those, the mixtures can be uh, homogeneous or heterogeneous. So we can have an alloy, or we can have something that is definitely clearly seen. Two things here: you have